Okay, so the second homework in this unit is about symmetry, like mostly symmetry of a square, and in general symmetry types and composition of symmetries. So you have three types of symmetries, two types really. One's rotation and one's reflection. The third type comes in if you break up the rotation into two parts, like a trivial symmetry, which is like trivial rotation by 0 degrees, or non-trivial rotations. So essentially there are just two types of symmetries, rotations and reflections. We'll denote by I the trivial rotation, which means that you don't do anything to the figure, and we denote by little r rotation. So these can, depending on the figure, these can denote like half turns or 1/4 turns, 1/3 turns, 1/7 turns, or something like that. And then we denote reflections by M1, M2, M3, where the MIs denote the axis of reflection. Now, when we say composition of symmetries, it means that we apply one symmetry transformation after another. So another notation is that this XOY, if X and Y are two symmetries, like they could be some rotation or some reflection. So if X and Y denote some sort of symmetry transformation, then this notation here, XOY, which is read as X of Y, therefore the little o. So X of Y means that you apply Y first and then apply X. So you read it from like right to left. So if you see, even in general, if you see functions f o g x, that means it's like f of g of x. So you apply gx first and then you apply f. So this is kind of like that. Now, some common like basic key rules about compositions of rotations and reflections. So it kind of behaves like positive and negative. So just like you have with multiplication, like positive gives you a positive, negative also gives you a positive, and then opposite signs, positive negative gives you a negative, negative positive gives you negative. So okay, let me switch these. Yeah, so it's something like that, where if you have like a composition of two sort of rotations, then the resulting transformation is also a rotation. Similarly, if you have two reflections and you compose them, like you apply one reflection after the other, in other words, if you reflect a figure about an axis and then reflect the resulting figure about another axis, then also you get a rotation transformation. On the other hand, if you compose two different types of symmetries, like if you compose reflection and rotation, then you get reflection. Note that in general, the order of composition matters. So in general, x of y is not the same as y of x. So it does matter what transformation you apply first, whether you apply y first or x first. It sometimes, like in general, it makes a difference. Then you would see something like x to the n, which denotes the composition of x with itself n times. So you keep applying the symmetry transformation x to the figure n times. X inverse denotes, or like x to the -1 denotes the inverse of the symmetry x, which is just another transformation. Like composing with x would give you the identity transformation. So basically a reflection, an inversion, or like an inverse of a transformation is another transformation which, when applied on top of the previous one, gives you the original figure back. So for example, with reflections, they are self-inverses. Meaning that if you apply a reflection about a given axis, let's say M1, and you reflect the resulting figure back about the same axis M1, then you would get your original figure back. So this is what I mean when I say reflections are self-inverses. Then x to the negative n denotes x to the n, or like the inverse of x to the n, or n times composition of x inverse. They're both the same thing. Finally, for any symmetry, if you compose it with the trivial symmetry, you get the same thing. And doesn't matter if you apply the trivial one before or after. Since the trivial symmetry doesn't do anything, if you compose x with the trivial symmetry, what you're basically doing is you're applying trivial symmetry first to the figure, which doesn't change the figure, and then you apply x, which is same as applying x. Similarly, if you apply x first and that changes the figure in a certain way, but then if you apply the trivial symmetry on top of that, it doesn't change anything, so that's x again. So these are some rules that we follow with composition of symmetries. And then you also have symmetry types. So there are two types of symmetry types. You have dn and cn. This is called the dihedral symmetry. This is called cyclic. And the little n is for the kind of shape for which we are looking at the symmetry. So this is the symmetry type of a regular n polygon. N polygon means a polygon with n sides, and regular means that all the n sides are of the same length. So this usually has n rotations and n reflections. And the n rotations include the trivial 0-degree rotation. For cyclic, Cn, this is the symmetry type of regular n pinwheel. Okay, so a pinwheel looks something like this. So this is a 3 pinwheel. Then you could also have a 4 pinwheel. Oops. A 5 pinwheel, 6 pinwheel, and so on. And I think you already know what polygons look like. So this could be a 3 polygon, a 4 polygon, a 5 regular polygon, and so on. Okay, now this involves only n rotations and no reflections. Because if you look at these pinwheel figures, you would see that there is no axis of no axis or no line about which this figure is reflective. So yeah, they don't have any reflection symmetries. They only have rotational symmetry. So if you rotate this 1/4 turn, you get the same figure. If you rotate it 2/4 turns, you get the same figure, and so on. Okay. Now let's start with the homework. You're given like one of the most important figures is the square. So it has this is its complete symmetry list. So you have the trivial one, you have R. Here R is clockwise rotation by 1/4 turn, so 90-degree rotation clockwise. And then R squared would be 180-degree rotation clockwise, R cubed would be 270 degrees. And then you have these 4 lines of reflection, M1, M2, M3, M4. So these are all the symmetries of a square. This you can denote as D4. Symmetries of a regular foregon, which is a square. Okay. Now we have to calculate the following composition. So I think the easiest way to do this would be to first fill out this composition table, at least for starters. Later on, when you are well versed with this topic, you can do this directly, but initially maybe let's do the composition table first. So the way we fill out this table is that you do row composed with column. Okay, so here you do I composed with I composed with R, I composed with R squared, I composed with R cubed, and so on. But we just discussed that if you compose the trivial symmetry with anything, you get the same thing. So what you'd get here is I composed with I is I composed with R is R, I composed with R squared is R squared, and so on. Similarly, this column here would also be the same, because R composed with I, R squared composed with I, and so on. These would also like result in the same composition. So you have R squared, R cubed, okay. Now R composed with R is R squared, R composed with R squared is R cubed, R composed with R cubed is R to the 4, which is like a 360-degree rotation, or 1 full turn, which is I again. Okay. Now R composed with and similarly these are also easy, so let me complete this little part first. So R squared composed with R is R cubed, R squared composed with R squared is like a 180-degree rotation followed by 180-degree rotation, so that's again R4, which is trivial. And then R squared composed with R cubed is actually R to the 5, but you can write that as R4 composed with R, which is the identity composed with R, so that's just R again. Right, this is because R squared composed with R cubed is 180 degrees composed with 270 degrees, which is like 450 degrees. Sorry, I think I messed up. It's not a good idea to do it with degrees. You can think of it like this. So this is like 2/4 turns composed with 3/4 turns, which is like 5/4 turns, which is like 1 full turn plus 1/4 turn, which is 1/4 turn again. So there are many ways to think of it. The easiest is to see that R4 is identity. So you try to pull that out. Okay. Now you can do the same thing here for the rest of this little box. So R cubed composed with R is R4, which is identity. R cubed composed with R squared is R5, which is R. And then R cubed composed with R cubed is R to the 6, which is R squared. Okay, so what you do get here is identity R squared. Now let's try to do this row here, or like maybe I'll do miscellaneous boxes and you'll get the hang of it. So let's do this one here. Let's apply in this figure R of M1. Okay, see that M1 is reflection about this. So let me color the vertices so that you're able to figure out where they went, like what their initial position was and what their final position is. Okay, so R of M1 means apply M1 first. I'm gonna shrink this figure a little bit. So after applying M1, meaning you reflect about this vertical line, the pink one goes here, the orange one goes here, like the pink and orange flip, and the blue one goes in place of the green one, and the green one goes in place of the blue one. Now you apply your R on this figure, which is like 1/4 turn or 90-degree clockwise. So you get so the pink one moves here, the blue one moves here, like all of these would rotate 90 degrees clockwise. So the green one comes in place of the orange one, and the orange one comes in place of the pink one. Okay, so now this is your final figure after transformation. This was your original, and we want to see how we went from the original to the final figure. Okay, and this would be this would be one reflection, because it's a rotation followed after reflection followed by rotation. So this would turn out to be a reflection. About which axis is this reflected? It's this M2 here. So if you reflect this figure about M2, you would see that the green and pink would interchange, and the blue and orange would interchange. And the blue and orange would stay the same because they're on the axis of reflection, so they won't reflect. So yeah, you see that eventually after you apply R on top of M1, you get M2. Let's do one more. Let's do 2 reflections. Let's do M2 of M3. So I'll do this on the same figure here. So we are applying M2 after M3. So first you apply M2, and after reflecting about this M2, you would have the green one on top, the pink one on bottom, and the orange and blue stay in place. Okay. Now, after you apply M2, you want to apply M3, which is reflecting about this horizontal axis. So you would reflect it about this horizontal axis. So the bottom ones go on top. So blue comes here, pink comes here, and the top ones go on bottom. So green comes here and orange comes here. Now a reflection followed by a reflection should be a rotation. So this is your final figure, and let's see how we can go from this original figure to our final figure in one step, in like one rotation. So yeah, this is R. So if you apply R to the original figure, which is the 90-degree turn, 90-degree clockwise rotation, you would get this final figure. So M2 composed with M3 is R. So yeah, this is how you fill out the whole table, and then using that you can calculate this. So let's do that now. Okay, so first of all, we can get rid of all the i's because composing with the trivial rotation doesn't do anything. So this is r squared composed with m3 to the 4 composed with r to the negative 2 composed with m2 inverse. Now m2 inverse is the same as m2. So this is just r squared composed with m3 to the 4th. And let's do everything in one step. So m2 inverse is just m2 because the inverse of the reflection is the reflection itself. So this is m2. r2 is already in place. In the middle we have m3 to the 4. So once you do a reflection like even number of times, so you reflect about m3, then you reflect about that again, that brings you to the original picture. Then you reflect about m3 again, and then you reflect about m3 a 4th time, which again brings you back to the original picture. So this is the trivial one. And then r to the negative 2 is just r2, because r to the negative 2 is the inverse of r squared, and the inverse of r squared is something that would bring like it to the original position. So once you have like 2/4 turns, you need 2/4 more turns to go back to the same picture. So again, you can get rid of the trivial reflection. This would give you r4 composed with m2. But then again, r4 is like 4 times 1/4 rotations, which is the 360-degree or trivial rotation. So that's trivial. And then trivial composed with anything is m2, like is the same thing itself. So this would be m2. Now r to the r102 can be broken down as r to the 100 composed with r squared. R to the 100 can be written as r to the 4th composed with itself 25 times. But then r to the 4th is the identity transformation, which is nothing. And then this is just r squared again. Okay. for the second part, we will have to look at this table, and once you fill that out, we'll be able to do this. And I think I will talk about this live in class because this requires some attention. So yeah, let's continue in the actual class tomorrow.